All right, this is part two of the chapter 10 test review. I'm going to go through the two FRQ questions. If you're looking for the multiple choice video, that should be loaded as well, but it's separate. So, number 9, these are both pretty lengthy, so buckle up. Number 9 is saying that we're comparing two common pain relievers, acetaminophen and ibuprofen. The subjects were assigned randomly to take each one. And they recorded if they had like adverse effects or symptoms. Does the data provide convincing evidence that they differ? So it's going to be a not equal to. They differ in proportion of the people who experience adverse symptoms. All right, it's a test right there, not an interval. And we're going to use 0.05 for alpha. All right, so identify your proportions, folks. I know it takes time, it's wordy, but it is worth it, and you get points for it. So PA is the proportion of acetaminophen users, that's pretty much Tylenol, that experience adverse symptoms, and PI is the proportion of ibuprofen. I highly encourage use subscripts that match and they really help you keep everything straight. I found the two proportions, the statistics, the p-hats, just using the data. So you can see ibuprofen is like double pretty much. So it looks to me like it's probably going to be significant, but who knows? The null is always that they're equal. And in this case, the alternative is that they're not, right? Because it says, do they differ? Or you can write both of these as subtractions. If I take PA minus PI, if they're equal, the difference would be 0. If I take PA minus PI and they're not equal, it would not be 0. We need to find the combined P because when we do the test, that's what we're going to use because the null is that they're equal. You can see they're not equal, right? So we're going to essentially combine them to find a number in the middle. And that's what we use for the test. So I'm going to have 44 and 49 successes out of 650 plus 347, which is 93 out of 997. I did it ahead of time. It's about 9%. So you can see again that is in between these two. It was stated to be random. Large counts, 44 and 49 are from here and here. And then these two, I guess, have to add up to 650. And these two have to add up to 347. So that's how I did that. All of these are easily 10. Therefore, don't forget to say the therefore part. This is approximately normal. Don't forget that. All right. And then independence is shown by checking the 10% rule, multiply it by 10 for each sample size, giving you 6,500 and 3,470. That has to be less than, not greater than, the populations. And specify, this is the population of people that use acetaminophen, and this is the population of ibuprofen users. So conditions are all good. Check, check, check. The z-score, now show your work. Here's the formula filled in with the numbers, right? This is simply the difference between the two statistics. The formula has the minus 0 because the 0 is the null. In other words, how far is this statistic from 0? Remember, if we were to make a curve for this distribution, it would be centered at 0. And the numerator here, I'm going to actually calculate this, is essentially the test statistic. No, sorry, it's the point estimate. Negative 0.073. So we're getting a point estimate way over here at negative 0.073, and we're going to shade that, remembering that it's also two-sided. So 0.073 on the positive side as well, and we're going to double it. Okay. When you fill in the formula on the bottom, remember I'm using the combined proportion, which I found right here. again, because we're assuming they're equal. If you write this out, you're good, and then you can just run the test. Stat test, this is number 6, 2 proportion z test. I've already filled the numbers in. You can take your time, but you can see that you get a z-score, negative 3.80, and the p-values there as well. Don't look, or don't miss out on the times 10 to the negative 4 there. If you do, you think, hey, it's just 1.43, and not at all, okay? If you move the decimal from here, 1, 2, 3, 4, and write it out, it's practically 0. So this green shaded area is essentially combined. Both of these together are 0, pretty much. So what is our conclusion? Since p is really small and it's less than 0.05, we will reject the null. This is when we use the phrase, there is convincing evidence that the alternative is true, okay? So I wrote it this way, convincing evidence that the proportion of adverse symptoms differs between acetaminophen and ibuprofen. This is not the only way that you can word this. You could say there's convincing evidence that the difference between the two is not 0. Or you could say there's convincing evidence that there is a difference in the proportion, something to that effect. Don't say that ibuprofen is greater than, has more effects, because we're not testing that. We're testing just that they're different. B, we are going to find the margin of error for a 95% confidence interval for the difference between the proportions. You don't have to carry out all the steps. So here's the formula on the cheat sheet. Just a reminder, the first part just gives you the center or the point estimate, which I found already. That's, not that I even needed to find this, but I did. This is negative 0.073, okay? There you go. The box is the margin of error. So the z star is the critical value. It's 1.96. We get that by looking at our green packets. Table B, look on the bottom. We've got infinity is where the z stars are, and there's your 1.96 for 95%. Then notice here, when I do PA and PI, they are separate. I do not use P combined when I do an interval. I only use P combined when I do a test. So if we want to try to do this by ourselves on the calculator, what's going to happen here? I would start with the part under the square root. Plus 0.141. See if I can do this without a typo. A syntax error. I couldn't, delete, I don't need that parenthesis at the end. There, and then I need to square root that, and there I have it. So I'm getting, that would be all of the square root, and then I have to multiply that by this. So the 0.02 that you see, that's the standard deviation of the curve, the standard deviation of this curve, and I want to go 1.96 of those to capture 95%. So I think I'm getting that for my standard deviation. No, sorry, this is my margin of error. If you ran it on the calculator, this would be button B. You see my numbers are still in there. I just gotta go down, change the confidence to 95. And it gives me the interval itself. And I can kind of double check this way that I did my work right. There is the interval. If I want to find the margin of error, I'm going to do a minus b divided by 2, like a minus b divided by 2. So negative 0.032 minus negative, be careful, 0.1149, and then divided by 2. And there it is. It does indeed match. So maybe to drive this point home, I could write my interval as negative 0.073 plus or minus point 0.0414, which is, I'm doing more than you need to do here. I'm just trying to give you the full picture. The answer is here. It's just, that's your margin of error. All right, next FRQ. This one's about heart surgery, and they use beta blockers during surgery to lower a patient's pulse. They had a random sample of two groups, 30 patients each, so we're good with the CLT. One group got the beta blocker, and the other one got a placebo. Okay, so this is an experiment because they are administering a treatment to each group. The pulse rate of each patient is recorded. Okay, so the treatment group had a mean, so it's a t-test. Here's the mean and the standard deviation. The other group, the control group, the placebo group, had the pink numbers. All right, part A, find the standard error for the difference in the pulse rates. This is the formula. I'm going kind of crazy here with notation. I'm using B for beta blockers and C for control group. If that helps you keep things straight, great. It's not required, but it might help you keep it straight. So the beta blockers had oops, wrong number. I'm looking for the S sub x, which is the 7.8 squared. Sample size was 30 for both. And then the standard deviation of the control group was 8.3 squared. This isn't so bad to do on your calculator, all right? I think I'm hoping to get 2.8 is what it looks like. 7.8 squared divided by 30 plus 8.3 squared divided by 30. And then square root that, 2.08. Okay, booyah. Part B, construct a 99% confidence interval, okay, interval for the difference. Don't perform a full write-up. Thank you. Just show the formula and interpret it. So here's the nitty-gritty formula, right? This here is the difference in the sample means. I put beta blockers minus control group is the way I'm going to subtract. I'm just taking these two numbers and subtracting them. When you do this subtraction, you get negative 5.1. That is the middle of my interval. I do need to find my t star. And how do I do that? I need to know degrees of freedom. Both sample sizes were 30, so I do 29. Then I need to look on my green sheet for this. You'll need to know this for the test, by the way. So I've highlighted the row 29 for my degrees of freedom, and I'd come over to 95%. Oh, wait, sorry, 99% is what it said, right? 99% interval, and it's 2.756. That matches up what I've got here, right here. And then you multiply by your standard error, which, hey, I already did that. Oh, isn't that nice? I can just bring it down right there. So what is 2.756 times 2.08? That is 5.73. This, again, just like the one we did a moment ago, this is the margin of error for my interval. That is the MOE. And then if you add it and subtract it, you should get this. Now, let's just check on the calculator. Stat tests, we want a 2 sample t interval, which is 0, okay? And I've already got the numbers entered in there. You can just look at them, make sure they're good. They're not quite good. This is a carryover, I see, from the last question. So I think they're then good, and I want 99%. Enter. And then do not pool. Something doesn't look quite right. It just doesn't quite match what maybe I had to maybe I should just do this, huh? You don't pool, by the way. You'd never pool. And notice when you do that anyway, it's only changing the answers by 100th, so not that big of a deal. 65.2, 7.8, 30, 70.3, and 8.3. Oh, and 30, that's why. There we go. Now that looks better. It doesn't match this perfectly. You can see it's within like 2/10, and that's going to be good. You know, it's because I've rounded. Like this here has been rounded, which, believe it or not, is probably the difference in the answer here. So we're good. To interpret it, remember how we say that. Fill in the blanks to this sentence here. We are 99% confident of what? That the true, what goes in that blank here? Here's the key word for all of your conclusions. The true difference in the mean pulse rate between the beta blocker group and the control group is between these two numbers. Okay, takes time to write all that out. Maybe I didn't give you enough space. Sorry. All right, C, suppose we want to do a test. Okay, so we're going from an interval, scratch that, now we're doing a test. Does a beta blocker reduce the pulse rate? I'm going to label these again. So mu B is going to be the mean pulse rate for beta blocker users. And UC is going to be for placebo users. Of course, they don't know they're taking the placebo. All right, the null is always right here that they're equal. Or again, if you were to subtract them, you get 0. The alternative, it's leading us here. We want to know, does the beta blocker reduce it? Okay, so is it less than? Is the mean of the beta blocker pulse lower? Or if you subtract them in this order, think about it, it would be less than 0. Okay, random was stated up here. Random groups. CLT, we're good here because both groups were 30, which is just enough. Make sure you say, therefore, it's normal. Independence, both are size 30. So do we think that, well, when you do this, that's 300 people. Do we think there's more than 300 people that have had heart surgery and been on beta blockers and had heart surgery and not been on a beta blocker? I think so. But write that out, spell that out for both populations. Take your time. Then we'll show the work for the formula. Essentially, you subtract your sample means and you divide by your standard deviation. We've already done a lot of the heavy lifting because this is this number. We already did that. And 2.08 is this number. Look at that. So when I divide them, I'm going to get negative 2.45. At least that's what I wrote down, right? Negative 5.1 divided by 2.08. There we go. So that's this. Now, how does that lead me to a p-value? Let's do it both the easy way and the hard way. The hard way first. Looking at my degrees of freedom and my test statistic and looking at the packet. Okay, here we go. So there's my degrees of freedom. I'm looking on this row for negative 2.45. And it is between these two. It's really, really close to this one, but not quite. And if you follow these up, that gives you the two p-values that's between 0.01 and 0.02. So I wrote it as you would. P is between 0.01 and 0.02. The calculator is going to give us this, which is between these. So let's do it on the calculator just to make sure. Makes me feel better about my work when it agrees. Stat tests. This is a 2-sample t-test, number 4. Oh, you know what? I never named it. Hello, Fog. 2-sample t-test for mu B minus mu C. There we go. Look, I've already got all my numbers there. Look at that. The test statistic is negative 2.45, bada bing, bada boom. And there's my p-value, which is indeed in between 0.01 and 0.02. Feeling good about life. All right. Conclusion, P is less than 0.05, right? If you're like, what are you talking about? 0.017 is less than 0.05. Feeling good? We are going to reject the null again. So there is convincing evidence of what? Everything that comes after is saying this. There's convincing evidence of the alternative. And put that into words, that the average pulse rate with a beta blocker is lower, less than, smaller than, tinier than the mean pulse rate without beta blockers. Interpreting the p-value. Okay, start with this. If the null is true, if there is no difference in the mean pulse rates, okay, if there's no difference in the mean pulse rates, then the probability of getting two samples of this size, what do you mean this size, Spike? Size 30, of this size, that differ in mean pulse rate by 5.1 or more is 0.017. Where did I get the 5.1? Where did I get the 5.1? That is what these two samples differed by, right here. They differed by 5.1. Okay? I should probably say, I should be a little more specific. It was negative 5.1, right? So getting two samples of this size, I'm going to try to say it this way. Two samples this size, where the mean beta blocker rate, pulse rate, I'm going to run out of room, was 5.1 or more less than the placebo pulse rate. This is probably the most complicated way to write this, but there you go. Okay. Type 1 error, it could have occurred, okay? Type 1, again, is when you reject, where is it? When you reject the null, but the null is true. So what happened is we claim beta blockers lower the pulse rate, but in truth, they don't, okay? What is wrong with this is doctors are going to think it works. So doctors are going to prescribe beta blockers and they aren't really helping the patients. And that would be a bad thing. Let me just come back to this one for a moment. Like, right, if there is no difference between the beta blockers, between these two things, then 0 is the middle of the curve. We got a sample of negative 5.1. And what we're saying with the p-value is that the shaded region is 1.7%. So this nasty sentence is trying to say if there is no difference, if the curve is centered at 0, okay, then the probability of having two samples where there's 30 people in each sample and the beta blocker was 5.1 on average, 5.1 lower than the control group, the probability of that sample occurring by chance alone is 1.7%. All right, thanks for your attention, folks. Make it a great day and a great test tomorrow.